I thank all of you for attending this workshop that came out from a collaboration, a discussion in the framework of two projects that funded by the European Research Council. One is shear, fault and activation and earthquake rupture, and TECTONIC. And therefore, it was an evolving idea that came out on this online workshop. And what I am going to do is to introduce the workshop and the structure and to contribute to the general framework and the overarching questions that we would like to answer. And I am presenting these slides also on behalf of the people that worked with me in organizing the workshop. Chris, as PI of the TECTONIC project, and also Elisa Tinti, Elena Spagnolo, and Menandrin Meyer. Okay, so in the invitation that we have received, we try to clarify which are the motivations and objectives of the workshop. So the topic is a very appealing and interesting topic, which is the fracture energy and the mechanical work. And the idea is to have an occasion, an informal occasion, to share visions and results, as well as to discuss the interpretation concerning the energy necessary for the initiation and the dynamic propagation of an earthquake rupture. In what we should define what is a realistic fault zone. Moreover, most of you are well informed that fracture energy and breakdown work are usually defined, used, measured in different interpretive frameworks. Each of these frameworks is perfectly self-consistent, but sometimes we are unable to reconcile them and also to make them coherent with comprehensive observation from both natural and experimental fault systems. So therefore, I think that the motivation are quite clear, I hope. And for this reason, we divided the online workshop in 4 sessions. Today, which is the first day, we have 2 sessions. One is dedicated to discuss the geological observations and therefore the inferences on breakdown work and fracture energy. There is one keynote by Faulkner, and therefore we have time for discussion. And there will be a second session where we have the energy and work to sustain dynamic rupture propagation, mostly just with the opposite endpoint, so geology and the modeling, and where we have 2 keynotes presentation, one by David Kammer, another by Jean-Paul Ampuero, on the fracture energy in linear elastic fracture mechanics and dynamic rupture models. And we have also here time for discussion. Tomorrow will be dedicated completely to the laboratory experiments, therefore to the experimental setup. We have 3 keynote presentation by Greg McCluskey, Stefan Nielsen, and Chris Marone on the different setup in the lab, and therefore we have more time for discussion. And finally, the last day, we have a session dealing with the seismological interpretations of fracture energy and breakdown work. We have 2 presentations by Rachel Abercrombie and Elisa Tinti, and we have time for a discussion. So Chris already anticipated you that the workshop is intended to be informal, therefore we have possibility to ask clarification during the presentation, but as you see, the presentation have been quite short, 15 minutes on average. Therefore, the idea is to try to encourage the discussion and the contributions in the discussion. Already several colleagues announced and anticipated the intention to present 1-2 slides during the discussion in the different sessions. And of course, we invite everyone to contribute, presenting ideas, interpretations, and suggesting conflicting evidence. So that is the rationale for the structure of the workshop. Now, to introduce the today session, I would like to start discussing what is the geological evidence. The presentation by Dan and the discussion will further clarify, but the key questions that we are going to discuss is how the fault zone is in reality. The damage zone is often considered as an energy sink for the dynamic rupture propagation, and there are numerous papers and interpretations relying on the assumption that the energy lost in the fault damage zone contributes to the fracture energy, which determine not only the rupture velocity, but also the peak slip velocity of an earthquake. And here there are conflicting evidence. So is process zone versus sleeping zone models, damage caused by fully coseismic dynamic or quasi-static slip, in particular for small small amplitude faults. So these are the one of the ingredients of this coming from geology. And therefore there is the observation of considering the fault core, which has a finite thickness with gauge, with properties in terms of rheology, mineralogic and poroelastic properties affect both dynamic weakening and the propagation. And again, here we have presentations and models that explain the gauge, the shear fabric evolution, both in terms of localized fracture versus distributed ports and poroelastic response of a thick fault zone. And afterward, if we agree that we have this principal slipping zone that contain gauge, therefore, the idea is how much the bare surface that we use in the lab are a good proxy or representative of a shear zone, a principal slipping zone in reality, since we know that after some amount of slip, the gauge is immediately formed. So this is the realistic part. And this is session one that we would like to discuss. And there is a reason why we decided to start with the geology, because reconciling the geological observations with the measurements and the calculation from models and experiments from the lab is current still an open challenge. The second contribution is that I would like to give is of the discussion is that the earthquake energy balance, because discussing the mechanical work and the fracture energy deals with the energy balance. So we all agree that in general, the energy that is accumulated during the interseismic period, which can be seen as the change in the elastic strain energy, including elastic plus gravitational energy change, is given by the radiated energy and the energy within the fault zone. Now, these are energy, global energy, which are measured for the whole fault or for a point source. But if we move to see which is the energy density or the work density absorbed within a fault zone, we can assume that this the energy density is partitioned into the energy sustaining the rupture front propagation, the energy loss of fault, and then energy dissipated on fault. Now, the point is that if we agree that somewhere below the slip weakening curve, these energies are seated, the problem is where are they positioned, how they are partitioned, can we quantify this? And in particular, if we find a way in which we can agree, and if we agree, for instance, that off fault with the damage correspond to the fracture energy, therefore, this could be an amount of the energy sustaining the rupture propagation. So there are several models. Each one is perfectly coherent from the inside its own framework, but still, I think that we have issues to be solved and clarified to understand the earthquake energy balance. And of course, discussing about frictional work and fracture energy is one of the overarching goals. The same will be the discussion of the breakdown. So in general, we use a different, let's say, mechanism explaining the coseismic rupture propagation. One is fracture and the other is friction. Zev, Reches will discuss further, will contribute. But to me here, the point is my message is very simple. So while the two approaches are mathematically equivalent, they are completely different in the description of the rupture process. In one case, we have a process zone at a given scale. In another zone, there is a breakdown zone of a slipping zone at another scale. And therefore, the question is, are these representations alternative, or they can coexist at different scales? And this opens the idea of what is the scales, because we have a macroscopic scale, which is where it is the scale at which we usually describe the friction and the frictional models. And the macro scale processes control the fault response and the shear dynamic reduction of shear resistance at the sides of fault patches, which are from meters to kilometers, or at the scale of the bulk of the fault core. And moreover, in these macroscopic and phenomenological approaches, the shear stress at the crack tip is finite. The energy dissipated at the tip depends on the adopted constitutive laws. On the contrary, we have the micro scale, in which these are processes that affect either the rupture and the slip episode at the scale of the rocks composing the material composing the gouge, or also at the scale of the asperity contacts, if we have two surfaces in contact, which are completely different, range between micrometers to tens of millimeters. And in this case, also the fractures inside the process zone of a microscopic representation of a propagating rupture fronts are also defined at this microscopic scale. And in linear elastic fracture mechanics, the stress at the crack tip is arbitrarily high or infinite, singular. And finally, there is an intermediate scale, which is the same that we use to define the damage zone of the fault core. And here the issue that the geology are trying to claim, both with observation and with experiments, is that the shear fabric evolution during the earthquake initiation and dynamic propagation controls the shear stress evolution and the slip velocity. So again, together with the geology and the issue of fracture and friction, there is a clear scale issue that we should consider in discussing our interpretative frameworks and our modeling attempts. And this, of course, not only it is a scale issue, is also the reason why we divided in this workshop the geology, the seismology, and the laboratory. And we should keep in mind really the scale. Finally, I want to discuss that if we are going to make a sort, I call it this, a zonation of dynamic breakdown, because if we plot the shear stress evolution as a function of the position in the crack and the displacement, at the crack tip, we have a process zone just behind, in front of the head, the crack tip. We have the breakdown zone, which is the zone where we have the shear stress degradation, and therefore we have a slipping zone. And the question is, are these problems completely scale independent? And therefore, it is the amount of energy dissipated in each of these zones that will make the difference? Or is the problem scale dependent, but there is one scale which is dominating all the others and controlling the breakdown process? Or even worse, is the problem scale dependent and there is no hierarchy among scales, which means that we are even not allowed to make an average, a spatial and temporal average? So I think that during the workshop, the issues of referring to different zones should be considered and taken into account. So to conclude, to respect my time, I think that there are several overarching questions that I hope we can try to address during these days. And I remind you that the idea is to try to verify the interest for organizing a workshop in person next year with more time and more the possibility to discuss. And the questions are the following. How the shear stress vary with slip during an earthquakes? What fracture energy is implied by shear stress versus slip and relation, which is how we can interpret the area below the slip weakening curve. What physical mechanism govern dynamic weakening during slip? And does fracture energy scale with slip, or is it a material property? And are we discussing the same parameter when we discuss the material properties against the fracture energy scaling? And are the mechanisms governing dynamic weakening of small magnitude earthquakes where we have millimeters or even smaller than millimeters slip amplitudes, but with the same stress drop than the giant earthquake? So are the mechanisms the same? And finally, how to reconcile the scale dependence of seismological fracture energy and the breakdown work with the constant stress drop scaling of seismic moment. I think that you share that these overarching questions are important for us. And I really wish you a stimulating participation. And I really like this picture that I took from Pablo, where sometimes we need to identify that simplification is important, but not necessarily simple solutions are the right one. And I stop here and I give the floor to Chris, and I really hope that we will have a stimulating discussion during these 3 days.
Fabulous, great start, Massimo. And I don't know if, the schedule was for Dan Faulkner to take over at this point. I haven't seen Dan yet. Dan, shout if you're here. And not hearing him right away makes me think, why don't we entertain some, let's say, questions from Massimo directly. We also have one presentation that was organized by Isaiah Vrekas. So first of all, a question or two for Massimo, or a point that someone wants to make. Use the raise hand feature. No one's raised their hand yet, so just unmute and tell us. Yeah, I guess with this group of people, it makes everybody nervous about unmuting and just saying something. Okay. Yes. Alice, please do.
Yes, I can ask a question. It's just a general question. I'm interested how these questions that you raised, how do they exactly relate to the two projects, the two large projects that are kind of getting together to organize this workshop? That would be interesting, I think, just to hear a little bit more about how all of these complexities and all of these different scales from the lab to the models, how do they actually relate to the overarching science questions of the projects?
Massimo.
Yeah, so for fear, but I think also Chris will respond for tectonics. But in fear, the problem is that we want to make a stimulation of an earthquake faults under controlled conditions. So the idea is to reach the fault in the underground laboratories in the Swiss Alps in Pedreto, and therefore to try to install a sensor and instrument to monitor the fault, and therefore to try to make the stimulation. But the stimulation is not just to trigger some seismicity. The idea is we want to precondition the fault and to try to understand, to measure which is the mechanical state and to see how the fault responds. Therefore, the idea is to record the micro earthquakes. We are not allowed to generate an earthquake larger than magnitude 1 or 2. And the idea is, but to record with acoustic emission sensors that are calibrated, for instance, together with the lab. So at ATH in Rome and in Aachen, there are laboratory facilities where we want to study the acoustic emission. And at the same time to install strain meters and stress meters in order to try to define also the state of, let's say, the state of stress and the conditions. And of course, the idea is to answer to one of the questions about the small earthquakes, because if they really share the same physics than the largest one. So fracture energy is relevant because, as you can imagine, since we need to stimulate an earthquake, we need to manage the risk. And therefore, we need not only to do a lot of preconditions to determine the geometry of the target faults and the size of the target faults, and also the properties of the gauge that we have identified for the characterization. But it's also fundamental to try to understand how the induced earthquakes, if any, because there is also the possibility that not earthquakes will occur, they will propagate and arrest. So the idea is when you stimulate the fault, which is the capacity to be that the final earthquake will be a magnitude -6, -4, -2, -1, or 1. And therefore, we need to try to make also modeling with the dynamic modeling to make some scenarios that will be useful for the risk assessment. But the idea is really to understand how the fault behaves and the response of a fault. And this also allowed me to add a further issue to the questions that I just presented to introduce the workshop, is that we know very well that the fault respond not only in earthquakes, but we have a very complex fault slip behavior. And now which is the stress versus sleep relationship that will allow a slow sleep events instead of a faster quake? Are they different? So still today, we don't have so many observations, especially in the lab, that they are very different. So I think that understanding the way in which the energy budget and the fracture energy of the frictional work is important, not only for the project, but more general. And the same is in the lab for tectonics.
Awesome, very nice. Alice, do you want to follow up very quickly? I know you asked me as well, but I'm going to move us in another direction because I see Dan Faulkner is here, and in an attempt to stay, let's say, more on time, Dan, are you prepared to share your screen and
Yes. Sorry, I was a few minutes late.
Yeah, don't worry. Yeah, perfect. Yeah, Alice, I heard you also ask about the tectonic project, and there's time right after Dan's talk for a general discussion, so I'll add more at that point. But Dan, when you're ready to share your screen, go ahead.
I will do. Yeah, no problem.
Okay. Yeah. And maybe while that's happening, Alice, I'll just say that, yeah, the tectonic project is also, interested basically in the physics of earthquake failure. And if I boiled it down to 30 seconds, I suppose I'd say that it is, trying to understand something about why machine learning based laboratory earthquake prediction works and how we can use those techniques also to identify precursors and really understanding the physics of why it works at the laboratory scale as a step toward understanding how to make things work at a field scale. So,
sorry, I'm just going to have to leave the meeting because I just had to authorize Zoom to share my screen.
Okay.
I'll be like
fine.
A few seconds.
Zaya, are you prepared to share your screen and I can't do, Massimo, is that your screen we're looking at right now? Someone's sharing your screen. Is it yours still, Massimo?
It says Jim Rice.
Understood. Okay, thank you. And I suppose I just need to find him. Hey, Jim, nice to see you. And I suppose there's a way. There's so many people. I'm not used to this gigantic crowd. I suppose there's a way for me to unshare it for him.
Yeah, Chris, while you are solving the issue and we wait for Dan. Oh, here is Dan. Okay.
Okay. So Zev, I started to ask, and so at the end of this, we'll just invite you to share your screen and fire away. And so maybe people aren't used to, down at the bottom of your screen, there's a reactions button, a sort of happy face that you can click and raise your hand if you want to raise your hand that way. Puts you in a kind of a queue.
Okay.
Dan, we see your slides, and if you'd like to go into presentation mode, fire away. The floor is yours.
Sure, I'll make a start. That's great. Perfect. All right. So thanks very much for the opportunity, I guess, to cover just some thoughts, I think, on the perspective from the field with regard to breakdown energy or fracture energy. So I just plan at the moment to try to stay on message, I guess, and think about what the field tells us in terms of what might lead to the breakdown in mechanical energy when we get earthquake rupture. Okay, so first of all, I'll start with some background. I guess that some of this will be familiar to most of you, but just to make sure we're all on the same page, it will probably be a little bit of repetition, I guess, from what Massimo may have already said. And then I'll kind of break down what I want to talk about into on-fault processes. So stuff that's happening within the fault core, where earthquake slip is happening. So how field observations help us understand the processes going on within the fault core, and then just widen that to dissipative processes that are happening in the wider fault zone, so off-fault damage. Okay, so in the simplest way that you can possibly think about it, and I'm sure that many people will talk about complexities that sit on top of this very simple view. But if we have a reduction in shear stress over some kind of slip distance that happens as an earthquake rupture starts to affect a portion of a fault zone, the stress drop that we get from a peak stress down to a residual stress over some slip distance gives us the available energy that is there to drive forward the rupture process. The actual stress evolution might look slightly different to that, so shown by the bold black line just here. So the stress might drop from peak stress down to some residual stress, and then stay constant for a certain amount of slip distance. And really, the green triangle there is the fracture energy or the rupture energy, the breakdown work, whatever you want to call it. That's the energy that you need in order to drive your rupture forward. And what's left over when you take that away from the total available energy is the radiated energy. So we end up with these ideas of radiation efficiency, which is the ratio of these the radiated energy to the total available energy. And that affects things like the rupture velocity and all sorts of various bits. So that's what we're trying to understand here. And how does the field actually help us? So as I mentioned before, we're going to talk about processes that are happening on the fault, within the fault core, and also within this zone of damage surrounding the fault core just here. And I guess I just wanted to point out that this green triangle can be partitioned, I guess, into two separate energy processes. So one triangle is related to the energy for on-fault processes, and another one is related to on-fault processes. And whilst I promised you all that I was just going to try to stick to field observations just here, I think it's worthwhile noting that the lab experiments that we typically look at are often just made on forcing blocks which don't allow that off-fault dissipative processes to occur, and therefore we only kind of measure the stress evolution, if you like, of the red line just there, and we only characterize the fracture energy associated with on-fault processes in many experiments that we run. Okay, so just to remind you what fault cores look like. So this is one of the most famous faults, I think, in terms of just understanding fault zone structure. It's the Punchbowl Fault in California. So this is a type of fault structure which is quite narrow. So the fault core here accommodates, I think, around 40 kilometers of offset, and it's on the order of 50 centimeters wide, I think, on average. The picture on the right there just shows you let me just see whether I can get a pointer. There we go. So the picture on the right just here, it shows the fault core of the Punchbowl Fault. And I'll come back to this a little bit later, but it's relatively clay rich in comparison to the host rocks that sit either side of this lineament in California. But again, you can see that 40 kilometers of offset really accommodated on quite a narrow structure on the order of 50 centimeters or so. And if we dig a little deeper, this is something I'm sure will come up in the discussion. There is localization within that fault core itself as well. So individual ruptures are likely to occur on much thinner zones of localization within that fault core. So what do field observations tell us about those processes that can happen on the fault during earthquake slip? Well, there's obviously melting that can occur. So pseudotacholites have been recognized in the geological record for many years. So that these black kind of glassy melts that emanate from a slip surface. So this example is one of Julio's from the Adamello batholith, the Geological fault. And you know, we can tell an awful lot of information from these as well. So from the early work of Mackenzie and Brune in 73, and also Rick Simpson's work in 75 on the outer Isle thrusts in the Outer Hebrides. It's been known that you can play around with the numbers a little bit here and look at the heat that's required to melt the rock just here. And you know, given the area of pseudotacholite in comparison to the slip displacement in the field, you can work out that the average shear stress in this particular case in the Adamello gives you you know, an average shear stress, I think, that produced that melt of about 18.6 megapascals. There's other neat things you can do here, which Julio showed in his paper in 2005. You can look at the angle of the fracture relative to the slip plane just here, and get some idea of the rupture velocity here. So that the inference here is that this rupture ran at about 0.9 times the shear wave velocity through the rock. And there's other things that you can look at too, the directivity of the rupture, etc. There's quite a lot that you can pull out from field observations, I think, in situations where we've got melting like this. So obviously there's been a lot of interest, I think, in characterizing the mechanics then of melted zones. You know, so there's been a lot of experimental work that has followed up these field observations by many groups. So another observation, moving on to the right just here, is a picture of the MTL, so the median tectonic line in Japan, which is a major lineament there. And the fault core, again, is made up of very, very clay-rich material. So I use this as an example to kind of highlight that these kind of materials, the thickness of the fault core that we have just here, and the low permeability of these gouges, lend themselves extremely well to produce favorable conditions for thermal pressurization. So, you know, if we have a fluid saturated, water saturated fault core that undergoes fast slip, that will pressurize the fluid within the pore space. And, you know, given the permeability of these clay-rich fault rocks in many major faults like this that you see around the world, that will inevitably produce thermal pressurization, because the excess pressures will not be able to diffuse out of these low permeability materials on any kind of time scale that is commensurate with the time required for rupture propagation. So, you know, here's just some experimental data just showing effective pressure along the x-axis here, and you know, these are for all sorts of different clay type materials which you find typically in fault zones. And, you know, hopefully the thing you'll note from this is just that the permeabilities here are extremely low, on the order of, you know, 10 to the minus 19 to 10 to the minus 21 meters squared. And, you know, these are, you know, these produce diffusion timescales which are much, much longer than any earthquake timescale. So not a field photo, but again, this is a nice example of how chemical changes as well. So, you know, in the last slide, I talked about thermal pressurization. So another consequence of seismic slip and all of the thermal consequences that has with it is that you can dehydrate or devolatilize materials which are in the fault core too. So the picture I'm showing here is from the work of Nick Brantut, where he's got 2 cylinders of gypsum in this case as well. And you can just see at the edges just here that there's a color change from the kind of white or lighter colored material to darker colored material here. And what we're looking at there is a reaction front where the gypsum, which is being slipped at seismic slip speeds, about 1 meter per second, is dehydrating. And the important thing here to note is that that is buffering the temperature on the fault surface just here. So it's equivalent to putting a pan of water on your hob, boiling it up or heating it up to boiling. You know, the water there will buffer the temperature to 100 degrees centigrade until all the water's gone, and then the temperature will increase significantly. And the same thing can happen, the buffering of that temperature for hydrous or minerals that contain volatiles. So, for example, you know, carbonates that may give off CO2, etc. So, as well as the pore pressure effect, we have a buffer of the temperature because of this chemical effect as well. So, something else we see in fault zones is that we get intense comminution as well. So we get very, very fine grain sizes in the cores of fault zones, and particularly in these very localized zones that may host earthquake ruptures. So, you know, this is a study from the Chesters and others, which looked at in the TEM scale just here, the sizes of grains that exist on these very localized zones within fault cores. And they are nano-sized particles that you get. So, you know, just looking at grain size distributions here, they were able to say that reducing grain size down to these nano-sized particles represents a pretty significant energy sink, which is going to feed into that fracture energy. Samis and Benzayan suggested, or looked at these kind of things. You know, they looked at literature from the powder industry and asked the question: is there a grinding limit for these? There is. You know, it's hard to produce particle sizes which are much smaller than a micron in this case, and they suggested that perhaps shock loading or subcritical crack growth were mechanisms that could lead to grain sizes which are down to the nanometer scale. But again, getting below that grinding limit of around a micron requires a fair amount of an energy sink. So I think it's worthwhile just pointing out that all of these things are highly coupled processes. You know, a good example is that chemical one, I think, where you produce heat, that heat gets soaked up in producing some kind of phase change, and that will limit or it will certainly affect the stress evolution, I think, that you get with slip and therefore the fracture energy. So this has been suggested before. So on the left-hand side are some experiments run by Stefan Nielsen and co-workers, where they looked at the fracture energy as a function of slip, and they stopped their experiments at various points. And what they found is that these thermal weakening processes, whatever they may be, lead to greater and a greater amount of fracture energy the bigger the event size is. So the more slip you have, you reduce the dynamic shear stress, and that will produce a larger kind of red zone just here, which is the fracture energy. So Vieska and Garagash, looking at natural data as well, showed the same kind of thing. So what we're looking at on the right just here is the fracture energy as a function of slip, again for a number of natural events, and they show this increase in the fracture energy with slip, which is telling us that you know, the size of the event somewhat affects the stress evolution and brings about different amounts of fracture energy in this case.
Dan, Chris, just chiming in to say, let's keep on schedule to be just a couple more minutes, if that's okay with you.
Sure. Okay. Thanks, Chris. Yeah. So okay. So I'll just briefly talk about off-fault processes as well now. So we've covered the on-fault ones. So again, you know, the damage zone, this zone of fracture surrounding the fault core, represents again another energy sink in this case. I'm sure we're all familiar with diagrams like these, just here, which shows the increase of fractures as you go towards a fault core. The damage zone consists of lots of different types of damage, from brecciation to microfracture, and these, are prevalent at different depths, I think, within the Earth's crust. And the scale of damage as well takes different amounts of time to heal, I think, over time. So just thinking about the scaling of these things a little bit, this graph here just shows the damage zone width against displacement for a bunch of small faults that we worked on in northern Chile, and also a compilation of data from Savage and Brodsky, shown by the grey shaded area just here as well. And what we see is we see this increase in damage zone with displacement. If we just think about why that might be, it might be because as faults grow, they host larger earthquakes, and those earthquakes produce extra damage around that. But faults are also rough too. So in a recent study that Yuval Tal and myself did, we looked at typical fault roughnesses and looked at whether the damage zone could just be produced by quasi-static slip on these rough faults. And I think if you look at the bottom graph just here briefly, the black open dots are the field data, and the brown ones here are a quasi-static model with typical fault roughness properties measured from the field on there. And it picks out the scaling pretty well. And if you add in some rupture dynamics to that, then typically you end up with damage zone scaling, or you end up with damage zones which are too wide for the amount of displacement, at least for these small faults that we observed in Chile. So I think it's an open question about how the damage zone the fracture is produced, whether it's produced quasi-statically or whether it is produced dynamically. So a type of fault rock which we're fairly sure, I think, is produced dynamically is pulverized rock too. So this was recognized, has been recognized in the last 20 years or so, where a lot of the intact macroscopic properties of the rock are retained, so you can see individual grains, but these grains are shot through with fractures, so they've just been shattered in situ in this case. And this example from Tom Mitchell's and co-workers' work have shown that these pulverized zones can extend for several hundred meters in some cases away from fault cores as well. So we need to think about how these might be produced, I think, by earthquake rupture. So yeah, just to summarize, just there, hopefully I've just given an introduction, I guess, to the kinds of on-fault processes that we can think about, I think, from looking at real faults in the field, also off-fault damage and how that can help us to understand these processes. And just to remind everyone again that these are highly coupled processes, and the modeling, I think, is just starting to produce these elastic models are starting to include spontaneous damage, I think, which can have an effect on the rupture propagation. And I think this is something that will be prevalent in years to come. So I'll leave it there. Hopefully that's given people enough to think about and start some discussion, I think, for this session. So thank you very much.
Fabulous. Thanks a lot, Dan. Listen, let's make this a little more active. The active part for you is to unmute yourself so that you can thank Dan for doing that. And use the raise hand feature to get a discussion going. While that's waiting to happen, I'll thank Dan personally again and point out that it was only a few days ago that he was asked to do this, so he's managed to pull this together in an incredibly short period of time. Vito, please.
Hi, Dan. Thank you very much for your presentation. Gives us lots of insights. So one question I wanted to ask you is, how do you reconcile the fact that in some cases you observe pulverizations at hundreds of meters away from the fault? In some other cases, you may almost say that damage is localized on the fault with much less damage away from the fault?
That's a really good question. I'm not sure I completely know the answer. You know, people have suggested, I guess, that pulverization can take place during super shear ruptures, where the stresses might just be elevated around the rupture tip and stretch further out into the country rock. So, you know, super shear doesn't always happen. So that's maybe one reason. But you know, I guess one distinction, you know, the on-fault processes, that's where the shear is actually happening, and that's where displacement is accommodated. And I think the deformation that happens, you know, tens to hundreds of meters away from faults, in many ways, will be produced by those well, the elevated stresses around the rupture tip, but they actually don't accommodate much of the shear displacement during earthquake rupture. So, Chris, how do you want to place as well? Because you know, there will be better people qualified than me, I think, to answer some of these questions too. So, so please feel free to chip in. I think anybody, if
yeah, I think exactly right, Dan. I mean, because you know, people are asking you a question, you respond, or you know, anyone. Georg Drazen.
Yeah, Dan, thank you very much. Very nice overview. Now, the question that I would like to throw actually in the audience and to you is to what extent we are really sort of moving in the same conceptual framework, or whether we are comparing apples with pears, right? I mean, all the processes that you described that contribute to what we call, quote unquote, fracture energy. So all the processes that contribute to dissipation in this complex scenario are probably different from what a fracture mechanics person would argue what he would see or she would see performing a K1C chevron notch type experiment.
And maybe it's perfect for Jay Feinberg to respond to that, unless you want to go in a different direction, Jay.
No, I think that's a great comment. I think the scaling is important, and I don't know the answer to that. In other words, fracture mechanics would tell us that if, as long as we have small scale yielding, in other words, all of the dissipation at the is at a conceptual point near the crack tip, and there's some region where you have a singular field beyond that, then you really don't care what's going on in the cohesive zone or the process zone. I mean, that's but the scaling, I think, is very important. So does the fracture energy or the breakdown, okay, I have some comments about what the difference between breakdown energy and fracture energy, but is this, you know, what's the proper scale in the laboratory? And I think I know what we see, and I think everyone else sees that does the types of dynamics experiments that we do. Basically, the slip for one fracture event is on the order of a few d sub c's, or the order of the roughness, a few times the roughness, like Onaka saw years ago when he buried the roughness. So what's the correct roughness to think about in a fault? Is it really the 50 millimeter or 1 millimeter very small zone where the Chester and Chester saw? Or is the roughness something like, or the relevant scale, something like the distance between barriers, between strong barriers or something? So I'm throwing it out there. I don't have an answer, but at least I know what fracture mechanics would tell me. One quick comment about the difference between the breakdown energy and the fracture energy. As I understood from Massimo's introduction, the breakdown energy is the scale at which all of the d sub c's that happen to be slipping or undergoing slip. So the fracture energy would tell you that there's a very clear connection between that macroscopic scale and the microscopic scale, which we call d sub c or something. that defines the cohesive zone. And that's just this breakdown energy or breakdown scale would be the ratio of the rupture speed and the slip speed times this d sub c. So I think they're the same things, but we just have to make sure if we want to speak coherently with one another that we're using the same terminology.
Yeah.
And skål.
Perfect. Bin Hawaii, please.
Thank you very much. I'm just curious, how much energy is dissipated off-fault compared to on-fault dissipation? What's the percentage? Do we have a current understanding of that?
So, well, I think probably the best estimates we have are from the Chester's work on the punch bowl fault. So in 2005, they looked at the fracture surface area, I think, in the fault core versus all of the fractures totted up in the damage zone. And I think their conclusion is that there's more fracture surface area within the fault core, given these nano-sized grains that exist there. So their inference is that most energy is dissipated in the fault core rather than the damage zone, which would seem to make sense. And then there's been some recent experiments, I guess, as well. The UCL group have done some estimates there of the energy sink represented by the propagation of fractures through samples. But again, I think there might be some scaling issue, I think, with looking at those experiments and taking it to the earthquake scale.
Thank you very much.
Georg, did you have another point that you wanted to come back with?
Me? No, not at this moment.
Okay, thank you. So I raised my hand so that I could ask Zeev to present. And maybe, Zeev, if you're ready to share your screen, we can ask Dan to stop sharing his.
Okay, I can
do that.
Oops.
Okay, and Tom Mitchell, would you like to ask your question while Zeev is getting himself ready?
Hello, can you hear me?
Yes.
Sure.
Yeah, so I was just coming back to the first question that I forget who asked it now about the pulverization. The idea of why we get big zones of pulverization and then small zones of pulverization, it's an important one. And I think that the key point is that firstly, we only tend to see these huge zones of pulverization on faults that tend to have regular magnitude 5 or big earthquakes. And the second thing is that what we now know from experience and also careful field studies of faults of varying displacements that show pulverization, that the pulverization is cumulative. It's not this instantaneous boom, super shear rupture.
Yeah.
And so what also happens is that there's also, maybe this is a topic to come back to later, but there's some really important feedbacks here in terms of the rupture dynamics. And so if you assume that all the damage is from a high strain rate rupture, right? If you got a very stiff thing and then you have a single rupture, you can have a lot of very localized damage, but then the elastic moduli changes, okay? So if you then map out the strain rate from the same rupture of similar speeds, the next time the strain rate is going to be higher further out, okay? So you're going to get damage wider and wider. So there's going to be a feedback on the changing elastic properties, lowering the strength of all. So yeah, that's the only thing I want to add on that.
Massimo, did you want to make a point? And Zeev, please go ahead and share your screen when you
Okay,
I wait.
Oh, okay.
Yeah, okay.
Do you see it?
We do. Nice and big around it. Probably need to go into presentation mode.
Okay. Basically, I'm referring to experimental work that I was busy in the last few years. And this is focusing on the weakening. What is the source of the weakening of the stress drop? And by comparing experimental work from two different types, the experimental in which we measure the stress drop using high frequency 1 megahertz measurements, seeing what Jay and his colleagues and many others saw the oscillation, and in the super shear case in the experiments, we see very quick weakening under very low, very small displacements, sub-millimeter displacement. This is just the stress drop. Here is the energy associated with the weakening. This is in one of those events, and the pinkish area is the energy, just due to the stress drop is substantial, but the time is very small. The distance is very small. Therefore, we have a very small amount of energy. This is from a typical steady state experiment in which the weakening occurs after a meter or two, and therefore we get relatively high energy. So what we did is something very simple, comparing the efficiency of weakening in experiments of different types. So what we see here is distance going from 1 microns to 14 meters. Weakening is increasing upward. So the experimental fault is at 0 strength at the top, at full strength at the bottom. And on the left side in the green frame is the results of rupture experiments of multiple people, including even the experiments of stick-slip experiments of Byerly and Brace and Parasqua and Rubio and so on. And basically what we see is that we may reach in sub-millimeter displacement 60 or 70% of weakening. Here on the left side in the red frame is the steady state experiments in high velocity, in seismic velocity. Here are rupture velocity on the orders of a Rayleigh wave or even super shear. And we see friction strength reduction, which is significant, but only after very large displacements. So, and in between we have experiments we ran with a flywheel and sticks and slip pulse, etc., which fall in between. Due to acceleration, it's becoming weaker, faster than in the steady state, but slower than in the rupture front. So the same goes with the energy associated, as I show in the same slide, in the previous slide. I will not show it. It appears in our recent paper. And basically the conclusion is that what we have, the rupture front, is more efficient by orders of magnitude in terms of weakening. So all the processes that we do, usually looking for a mechanism that Dan presented so nicely, the weakening, mechanisms of weakening due to the friction, is really not necessary. It's contributing further to the weakening, particularly for large earthquakes, but it's not essential for the weakening of the fault itself. The rupture front does most of the work, if not all of it.
Thank you. Massimo Cocco, were you going to add, do you want to add something right now?
No, my questions, Chris, was related to actually to a comment to Jay, but I was just digesting what Zev just said, because Jay was referring before to D sub C, but D sub C is not a constitutive parameter. So, and this is a parameter which is really not completely measured and understood. So I still am not, I do not understand how much it is just the D sub C that will tell us how much we can switch. Zev now presented a different reasoning on the fact that tip processes are dominating the weakening, which could be reasonable, provided that, of course, we demonstrate that the work that is absorbed during sliding on a breakdown zone, which could be hundreds of meters wide, it is not contributing to the weakening. So I agree that the process can dominate for creating damages and off-fault dissipation. I think that what Dan is presented, and this is a comment to everyone here, is that Dan concludes that from geology, we have multiple highly coupled processes that can explain the on-fault dissipation. Now, this is what geology tells us. Now, if they are multiple, means that they can compete each other in a way which is completely unknown. And there is a scale at which they compete. Let's make the most clear example: flash heating and other type of viscous resistance to shear. Okay, so they are coupled, but we don't know which is the transition, how the mechanism works in series or not, how they compete, if there is a transition at a given slip or there is a range of slip values where the transition occurs. So even if I agree, I need to digest what Zev presented. From an energetic point of view, I would kindly to ask him to quantify in terms of energy dissipated, why the sliding is dissipating less than the process zone.
Oh,
so
no,
in the plot that you've shown, there is no quantification of the energy absorption. It is just a measure of the slip.
Oh, yeah, that's true. I didn't show that graph. It appears in the paper, but basically we compare the energy measurements in stick slip events of Faulkner et al. With those of Di Toro in the steady state friction. And basically it's about the stick slip consume about 1 order of magnitude less energy than the steady state friction. So obviously, we know that the breakdown of earthquakes takes only 5 to 6, 7% of the total energy, and the friction takes the bulk of it, 70, 80%. So the friction is a big consumer of the energy, but in what we think, it's only smaller contributor to the weakening. So these are two, conceptually, if we separate the fault zone to the rupture zone front and the back in the wake of the rupture front, we have the frictional zone. Then the weakening at the rupture front is the main driver in terms of weakening, but the energy is consumed in the back, particularly when the displacement is large. Even if the friction is very low, it's still large displacement, so it requires a lot of energy.
Okay, so it's a great place to connect back to some of the main points that were made by Dan, and maybe one thing to think about for the discussion later on today or tomorrow is whether there's an explanation of that connects to the critical weakening distance, the D sub C that Jay was talking about. Okay, now just to keep ourselves roughly on time, I'm going to ask Georg and Stefano if you guys have something quick to say it quickly.
Yeah, but I just want to support what Zev was saying. This is typically what we see in our experiments, that we have, practically in all the materials that we've been testing in stick slip tests, saw cuts, fractured faults, from Monterey claystone all the way up to westerly granite, we see the propagation of a rupture front that's associated with a stress drop. Yeah. And we get very different information from local stress drops calculated based on, strain gauges close to the fault compared to the bulk stress drop. So I would agree with I would agree with Zev and argue that, if you want to categorize it or schematically divide it up, there is a rupture part, there's a friction part in the process. Yeah. And it's in the friction where you have a lot of the, energy that we typically just calculate from our tests. So I fully agree with that.
Thank you. Stefano.
I have a question about it's more a curiosity, but for example, in this paper, the kind of rupture you have at the very beginning of a slip supposed to be more similar to a mode 3 rather than to a mode 2? Or do you think that in your setup, the geometry, the rotary geometry doesn't change this?
You're asking me. It's a rotary system, but because because of that, the rupture is limited to, it's initiated somewhere in the middle of the ring, and I would say it's more closer to a mode 2 rupture because of that, because the ring itself is fairly narrow.
Okay, thanks.
Okay, that's another great discussion point to keep in mind. Now, this is an experiment, running a workshop like this, and we're learning along the way. But David Kammer is supposed to be up. We're a few minutes behind our schedule from what we had published, but not too far off. Alice, Gabriel, and Francois Passelègue are the chairs in this next section, so I'll invite them to take over. Obviously, we'll all be here. But I think, David, you want to start to share your screen, and Alice, if you want to say something to introduce or...
Sure, I can do that. So we're taking over for session 2, which is energy and work to sustain dynamic rupture propagation, supposed to be 1 hour. And we have 2 speakers, David Kammer, who go first on fracture energy in linear elastic fracture mechanics, and Pablo Ampuero on inference from dynamic rupture models. And then we have a 30-minute slot for discussion that Francois and I will lead. And we already have, we know that Valère Lambert will present some slides. Francois and I also both prepared some slides. So we make sure that these 30 minutes will be busy too. But now we start with David, and I just hand it over to you.
Perfect, thank you. Can you hear me?
Yes, I hear you.
Okay, good. So first of all, I hope the line will hold. I mean, actually attending a conference, I'm in my hotel room trying to use whatever internet I have. So the title that I got assigned to was Fracture Energy in Linear Elastic Fracture Mechanics. I allowed myself to add a little extension to it as applied to the onset of frictional sliding. And so really the objective I have is I'm going to put it down to the basics, neglecting much of the complexity that has already come out of the discussion, to just bring down this discussion to the definitions. Because I would like to make a suggestion how we define fracture energy and break down energy which should not be the same. And I think it would be very important if you're able to use them consistently. And for that reason, if I can make my point, I will provide the slides online so that we have a reference anyone can go back to, and I created a link for that. So let's see if this actually works. Good. So let's start with linear elastic fracture mechanics. Initially, right, from the name, we know it is applied to fracture mechanics. And the question that was used to, or what this was used to answer is, does a crack grow? Now we have a setup just systematically here shown, and with an initial crack. And you're actually looking at whether this crack is growing by some dA, let's say. And really what we are doing is we are comparing 2 states. That's what we want to do. And if you want to do this, we need to make a few assumptions. I put one nice book for fracture mechanics, but there's many more out there. I think this one is relatively concise, that's why I like it, but there's many other resources you could use. So the assumptions we do is linear elastic material, okay, very easy. Then the very crucial one of small scale yielding, so that we have the separation of scale. This is what then will lead to the discussion whether we actually have this brittle type of failure or not, and all the complexity that we have been discussing may affect this assumption here and whether it is applicable or not. And then we have an assumption is the crack surface is traction free. That is usually just implicitly assumed in fracture mechanics. And then often it's 2D, but this is strictly speaking not actually required. And so now if we compare these two states, the way we decide whether we go from this state to that state is by doing an energy balance, where we have on one side the energy release rate, which tells us how much the stored potential energy is changing with this with the change in the crack length. And important to notice here is that this is a global quantity, and this is sort of the thing that is driving the growth, okay, the quantity that is driving the growth. And then this is equal to the fracture energy, which I call gamma here, which is the dissipated energy during the crack growth. And so this is typically a local quantity to some degree, okay, so we zoom in. And it could be a material property, it could be an interface property, it could be a bit more complex, as our discussions will show. But in the end, it's a local quantity that we need to consider. And then this is sort of the resistance against crack growth. Okay, and so we do these two comparison. Now, if I need to get this far away. Okay. If I want to get a few examples for those, let's say first we look at the energy release rate, which is this global property. A very simple example in fracture mechanics is the little crack of length 2a in a remote loading of sigma. And if you take this and you go through your inelastic calculation, you can determine this. This is very often assumed in many applications. But the key here is it's an infinite plate, remote, uniform, uniaxial stress. And you have some assumptions, plane strain, plane stress, that go into this, the Young's models here that we have. So you have the applied stress and the crack length. The a bit more complex or more general case is when if you apply the stress along the interface, but now have a variation in space, for instance, you can compute the energy release rate, which now looks very, very complicated. But actually, if you choose a constant value here, you will find this equation again. So we shouldn't get scared of that. But this is just taking into account the geometry and the large scale of the problem. And then this is opposed to the local property, the fracture energy, which you could think of as the cohesive zone at the crack tip, which may behave in some way where you have the cohesive stress that changes with the crack tip opening. And if you have a cohesive crack like this, you can determine your fracture energy through the integral of this curve, basically until infinity, right? But it's essentially this area over here. Now, what can you do with LFEM? Well, you can predict a few things. Number one is you can predict crack nucleation, where you say if you have the energy release rate is larger than the fracture energy, you're growing. And the very typical case that most of us have heard of before is energy release rate versus crack length, right? If we plot this, if you assume a constant fracture energy for like a brittle material, it is constant here. If you take back this very simple case that I showed you before, you get the linear growth of G as a function of the crack length. And so you find this cross-section from which on you will have growth actually to infinity. And that critical size here is the famous Griffiths length that we all have heard of. And so really you see how it comes out of this energy balance based on a few heavy assumptions. Then you can also use it to describe crack propagation. Now here you need to do a little bit more work because the energy release rate now is a dynamic one where you have, which you can, if you assume an infinite medium, approximate by the static one that we know from what we did already here, plus some dynamic known function. And if you do that, And let's assume fracture energy does not depend on rupture speed. You can recover how the crack will propagate at which speed, at which crack length, the so-called equation of motion. This is just one example when you have all the simple cases. But even if you had non-trivial growth of fracture energy with rupture speed, possibly you could solve this for your rupture speed and describe that behavior. And then finally, you can also define crack arrest, where the energy release rate becomes smaller than the fracture energy. And it's essentially the same thing as you do for nucleation, except that it's sort of, again, this point here, but except that now we're at some distance. So you need to have some sort of heterogeneity in the system, whether it is in the strength or the toughness or in the stresses, the load that leads to non-uniformity in the energy release rate. But essentially underlying, it's the same argument that we have in crack nucleation. Good. So now the point that I wanted to make here is that the fracture energy is really what is directly governing the crack growth, nucleation, propagation, and the rest. Now, can LFEM be applied? I don't see my own title because of the bar here somehow, but to friction, I assume it says. So again, we do the same thing. Does a slipping area grow, right? So now the system is the one that we are a little bit more familiar here with the shear load instead of a normal one, and we have sort of the slip area that in between stick area, and we're asking whether this part is growing. And here you could, again, if we do LFEM to apply this, we need to compare states. And if we compare states, then we, of course, need to look at the small scale, here the local one, where it's the same thing as before, just now in shear, which is a little bit more difficult to visualize, but you get the idea, right? And now we have the friction traction as a function of slip, for instance, just as an example, where you have some finite strength, and then you go down to some residual strength, which is non-zero. So now comes an additional assumption that we have to make here, which is that the residual friction is constant because the crack surface is not traction-free anymore. But now if you assume it is constant, you can, under many conditions, assume that this, or you see that it will lead to small-scale yielding, and so separation of scale is still valid. And so then you can do the same thing as in fracture, just slightly different, but it's underlying the exactly same thing. So the stress drop, which before was just the stress you had initially, because the surface was traction-free, now becomes a difference between the traction you apply minus the residual value. You can compute the energy release rate, which just is basically mode 2 instead of mode 1, and you need to use the stress drop here rather than the stress. And you can compute the fracture energy, which was the integral we had over here, but now applied to friction, you remove the residual friction over here. But other than that, this is pretty much the same thing. Now, of course, all this becomes more complicated, and I think Pablo will mention or talk about the rate and state friction, how this affects this just in a little moment. Now, can this be applied to laboratory experiments? And the question then really is, are the assumptions satisfied? And actually, to what we have seen, this really happens to work. Let me try again here. So one is, and I just point you towards the references. I can't explain you the details. I put out the references here where really the objective was to demonstrate that LFEM works. There's many, many more references out there that use LFEM to explain certain things. But here it's sort of, these are the papers that try to demonstrate that LFEM applies. So you can do that for PMMA, for granite. These are the references. I think Greg McClaskey will talk about some of this tomorrow. You can describe propagation speed in LFEM. You can describe arrest in laboratory experiments for PMA and granite. And you can describe nucleation, at least to some degree. I'm not sure if we're fully conclusive on that because we have some other evidence. But I think also Pablo will mention a few things about this in this next step. So really, if you're here, it seems like in large-scale laboratory experiments, it is applicable under like dry friction assumptions, and it works in a quantitative way. Now, is it still true For other systems, for natural systems, for like tectonic faults, well, we don't know yet. But if it was, it would be a very powerful way of understanding and describing earthquake mechanics. Now, I want to make one last point, which I think should bring us to this difference between fracture energy and breakdown energy. So the question is now, what if this assumption that the residual friction is constant is not satisfied, which likely is the case, right? It probably is not constant. Well, let's assume you have some friction traction that is now dependent on slip rate. You can do any rate dependent or rated state dependent law, actually. And if you turn this just into a traction of tau as a function of slip, you would see something that actually often looks very similar to linear slip weakening, except that it's not constant. The residual friction is not constant. And here I want to point to these two recent papers that are really working on this aspect and pointed out, that you can define this breakdown energy, which is essentially how we computed the fracture energy on the previous slide, and you assumed constant residual friction. But let's say now this is the breakdown energy, and the fracture energy would be then the part that is dissipated really in the local way, in the fast way. And the term used here is edge localized dissipation. And if you distinguish between the two here, you can actually, and this is what they showed, is that the rupture growth, hence nucleation, growth, speed, and arrest, are actually governed by this part of here, okay, by the energy release rate being equal to the fracture energy. And so I think what we should say is that the fracture energy is really the part, thinking back of fracture mechanics, the part that describes the growth, whether it's nucleation, speed, or arrest. And the breakdown energy can be anything that we can integrate below here, because that's what we maybe can measure very easily. But I think there's also ways to measure that. And that's the part that will matter for the earthquake as like a dynamic event. Maybe not for the global energy budget, but for what governs the growth. This is the part that matters. And so my suggestion would be, and this comes out of those two papers, that we define very clearly that the breakdown energy is the dissipation associated to the reduction in strength above breakdown friction, above heat. This shouldn't mean heat, but above heat. So this is just if you integrate your frictional stress over the amount of slip minus the residual stress, that is what is the breakdown energy. But this is not necessarily the part which will govern the growth. And so we should say that the fracture energy, following fracture mechanics theory, is the rupture-related dissipation that is associated to this edge localization and that governs rupture growth. And so, which is then being used in this energy balance. And now, of course, just to bring everything back, if residual friction is constant, then the fracture energy and this energy breakdown energy, are the same. But this is probably too heavy of an assumption. And again, I have all the reference in it. That's why I put it online. And if you want to use the QR code to get faster. Right now, you won't find anything because I want to adapt the slides if there's any input. But save the link and then you can use that as a reference if you want. I think with that, I'm done. And I'm happy to discuss, or I think we move directly to Pablo if I understood all right.
Okay, thanks a lot. So we can, thanks, David. So is there any questions for this? Thanks a lot for your really nice talk. So I see that Massimo has a comment probably or questions.
Yeah, I have a question actually. And yeah, I like very much, but therefore my question is very simple. When before we were discussing about rupture and friction. So what if, according to your distinction about the breakdown energy and the fracture energy, rupture is everything is occurring within the breakdown zone? Because when you plot that picture, Dave, you have a number of points that are slipping inside that area, also with the fracture energy. And therefore, perhaps the zone that you are referring to is not the process zone at the crack tip, but is a zone of points that are close to the crack tip, but they are sustaining the breakdown stage. This is what Zev was calling rupture before. This is
I think what you would call the process zone is really this edge localized dissipation. Now, it may be a little bit difficult to exactly define it. They are providing in their reference a one way that may be a bit difficult to measure, like experimentally, but it's really what is dissipated really fastly, very localized. And even if you have some additional dissipation that goes on because you continue to weaken at a slower rate, overall, this goes into the energy budget, but it will not affect the fracture growth. Hence the question of whether the earthquake is going fast or slow, whether it's going to arrest or not, right? And this localized dissipation, like a process zone is just one way of model this localized fracture, like the localized dissipation.
Yeah, thank you. I fully agree in this case.
Good. I'm surprised I was able to.
So there is also a question from Gabriel. You can go on.
Yeah. Oops. Yeah. Great talk, David. So I have a question concerning the this sort of separation of the fracture and the friction process related to stability. So the stress drops. You have a stress drop that is associated with the rupture propagation, but minus slip, which gives you a certain, if you like, stiffness. Now that's important when we discuss potential force imbalance. So what is your take on that?
I'm sorry, I didn't understand. So you have a stress drop and slip.
Let's assume we have a a slip process where a slip occurs and stress slip occurs over a certain distance, and you have a certain stiffness associated with that, and then you put this in perspective to the stiffness of your loading system. That tells you whether you have a force imbalance or not. Now, if the process really involves something that is sort of hidden in this dissipative process, which is the rupture, which occurs over a smaller slip distance, you would get a different stiffness. So what is the implication for the force balance there?
So if I understand you right, so we have to look at what length scale you're considering, right?
Yeah.
So if you're thinking of what Dan has shown in the beginning, this one-dimensional problem of your stress going down, the slip and the energy that you have and how much it is dissipated, really, if you do this, you're thinking of a single degree of freedom in a way. And so you're below a certain length scale associated to a rupture, okay? But if you look at a system that is larger than this nucleation length, the Griffiths length or something else, right? But some sort of length scale that you have there, if you go beyond that, you cannot think this way anymore because you need to consider the fact that you have a edge localized process. And so you have the crack propagating. And then the stiffness is really it's a different story about how whether you are unstable or not. It's not just a one-dimensional way of thinking, right? So it depends. If you have a very small experimental setup, you possibly can think that way. But if you go large, you need to consider the fact that you're concentrated. And then the stability is not just the stiffness stability, then it's the stability of the stress applied versus the size of your instability region or so.
Yeah.
I hope I was able to.
Yeah. Thank you.
Okay, so we have a question of Jane. Maybe Pablo, you can start to share your screen also. Perfect.
Just a quick comment relating to, again, the definition of breakdown energy and fracture energy, because it's very confusing. I'm bringing this up because of Massimo's comment. One process is happening. The crack is moving and there's slip occurring at the tip at every point, and that's D sub C or whatever. But then you can look at all of the points that are slipping at a given time as the rupture is propagating. And D sub C is related to what I think Massimo defined as the breakdown energy, not Dave, as this d sub c, this local slip, times the ratio of the rupture velocity divided by the slip velocity, which is a factor of 1,000 or 10,000. So they're the same quantities. We just call them different things. Just wanted to reiterate it, at least to explain it to myself. So
I agree with you, Jay. It's like, that's why it's confusing, but I think that's why we need a consistent language that we all are referring in the same way. And I think the definition that comes out of those papers, I think would be a very good basis for that. Not my definition, but I really like it. And I think it would be a good basis.
Yeah, but we should use this opportunity to clarify terminology among us. It is really extremely important for speeding up our future interpretations.
I agree with you 100%, Massimo.
Okay, so Pablo, you can maybe present your...
Thank you. Hello, everyone. I first want to thank all the previous speakers because I will be able to build up on the concepts they introduce, so they'll make it easy for me. I was invited to talk about fracture or breakdown energy in dynamic rupture models. So I picked a few topics to discuss today, more of as teasers to stimulate discussion. So I will talk about fracture mechanics for pulse-like ruptures, especially for long ruptures, emphasizing how that is different from crack-like ruptures. Then I will discuss also what we have learned so far about the contribution of fold dissipation in dynamic rupture models. And then close also with a discussion about the fracture energy produced by rate and state friction models and what does that imply for slow and fast earthquakes. So let me start with the fracture mechanics bit. As introduced by Dave, we have this fundamental result of classical fracture mechanics, which is the crack tip equation of motion, basically an energy balance, telling us that the fracture energy on the left-hand side during rupture propagation has to be balanced by the energy release rate of the rupture. And in the special case of a circular crack, that equation looks like this, where there are terms that depend on rupture speed. That's the time derivative of the rupture radius r, the stress drop, the shear modulus, and the rupture radius itself. And this equation has a form of an ordinary differential equation of the type time derivative of crack size is a function of crack size and other quantities that we can assume that they are known in this problem. So this ordinary differential equation can be solved to obtain the complete history of the crack growth from its nucleation, its propagation, and its arrest. So that's why this concept of the crack tip equation of motion is so powerful. Now, it works pretty well for crack-like ruptures, but we also know that there's another very important style of rupture, which might be prevalent for earthquake, which is a pulse-like rupture. So the difference between the two is shown here in these figures on the left. These are space-time plots of slip velocity for a crack-like rupture. As the rupture propagates, all the area inside the two rupture fronts continues to slide. That is not the case for pulse-like rupture. Behind the rupture front, soon after, there is a healing front that where slip velocity vanishes again. So the hypocenter will stop sliding before the rupture has even stopped. Anyway, so why is this different? Now in a pulse-like rupture, we have two unknowns. One is the position of the rupture front, and the second unknown is the position of the healing front. However, we only have one equation, which is coming from this energy balance, the G equal GC equation. So we need a closure equation, and this has been attempted in different ways. For example, by introducing additional assumptions such as steady-state pulses. Those are pulses that propagate at a constant rupture speed. So that helps us advance conceptually. However, those steady-state pulse into the models have some limitations. First is that they do not radiate energy to the far field, and that's an important shortcoming relative to seismology. And a second strange feature of the steady-state pulses is that they have zero stress drop. So that's also not very convenient to compare to real earthquakes. There's one situation in which a rupture can become a pulse, and yet we can obtain a crack tip equation of motion. So this has been obtained in recent papers with Hui Weng. The situation is the one where we consider a very large rupture, so large that it has already saturated its seismogenic depth, and it's basically propagating only laterally. And it does so in the form of a pulse, which you can see here now at this stage of the rupture. So it's a narrow region that is of sleep that is sweeping along the fault. For this particular case, we have obtained a crack tip equation of motion that can give us, like in the classical problem, the whole history of the rupture speed if we know the fracture energy and the potential stress drop along the fault. Something important here is that the width of the pulse, that is the lateral extent of this sleep zone, is smaller and often much smaller than the seismogenic depth in these models. So that's something important about the scales involved in the problem. And the second important feature is that the energy release rate depends on the spatial distribution of stress drop along strike, but only on that distribution close to the rupture front and within a distance to the rupture front that is smaller or much smaller than the seismogenic width W. So this is to say that the dynamics of a pulse that is constrained by a finite seismogenic width is mostly a local problem that depends on the local values of stress drop and the local values of fracture energy at a scale smaller than the seismogenic width. Now, let me make a second point here. Let's talk about off-fault inelastic deformation and how much does that contribute to the energy balance. So we've seen already in Dan's talk that there is significant damage structures around natural faults, and some of that may be produced dynamically during earthquakes, co-seismically. In 2005, Joe Andrews, and already in the mid-70s, he had done simulations of dynamic rupture with off-fault plasticity. And this was revived 30 years later by Joe Andrews himself in this beautiful paper in 2005, where we can see one of the results here in this figure on the left, which shows us the distribution of inelastic strain outside the fault during the propagation of a crack-like rupture. This is a bilateral crack-like rupture that's generated in two triangular-shaped off-fault plastic zones. Because the thickness of this inelastic zone keeps growing as the rupture grows, the amount of energy that is dissipated outside the fault per unit of crack advance grows also linearly, proportional to the crack size. It is plotted in red here on the figure on the right, and the on-fault energy, which in this simulation is given by slip weakening friction, remains constant, whereas the off-fault dissipated energy grows linearly. So eventually the off-fault dissipation overcomes the on-fault dissipation in this type of models. And this shows that this component of the fracture energy is scale dependent. He also showed in this paper that you can actually explain the rupture speed achieved by these ruptures by writing the energy balance that comes from the crack tip equation of motion by balancing the energy release rate to the sum of the on-fault fracture energy given by slip weakening friction plus the off-fault fracture energy given by the plastic dissipation outside the fault. So that is to show that these assumptions of linear elastic fracture mechanics seem to apply also in this particular case, namely that the size of the plastic zone is sufficiently contained within what is called the K-dominant field. So that's the area around the rupture tip where the square root singularity behavior is dominant. So what do we know about this contribution of fracture energy? There are some things that we don't know that we have established already, and some things that are still in progress. One of the things that is, I think, established by now is that we can theoretically estimate the thickness of this inelastic zone. We have proposed some theoretical estimators in papers with Shiqing Xu. Here are some comparisons between the numerical simulations in red and the theoretical estimation in the solid black line here of the thickness of the damage zone as a function of basically the initial stress on the fault. So that is something we have. However, we still don't have a theoretical predictor for the amount of dissipated energy outside the fault as a function of the relevant parameters, which are the rupture speed and the initial stresses. That is something we are making progress on in collaboration with Katya Molotskaya, grad student from MIT. We have been running dynamic rupture simulations with on very long faults, so much longer than their seismogenic width, including off-fault plasticity. So again, these ruptures become pulses very quickly. And as you can see in this example on the left, this is the rupture speed as a function of time. Rupture speed ramps up and it tends to a steady value eventually. And that steady value is much lower, it's significantly lower than the Rayleigh speed, which would be the limiting speed if there were no scale-dependent fracture energy. So this conceptually confirms that if you have a scale-dependent fracture energy, you can reach, it confirms one of the predictions of fracture mechanics, which is that you can reach a steady speed that is significantly lower than the limiting speeds, which is the Rayleigh speed on mode 2 and the S-wave speed in mode 3. So we are now in the process of studying what controls this limiting rupture speed as a function of the strength excess, as a function of the closeness to failure outside the fault. And we are also getting results about the ratio between the off-fault dissipation and the on-fault dissipation. And those ratios, at least in these pulse-like simulations, are substantial. They are, of the order of 50 to almost 100% here. One more topic here, which is the fracture energy associated to rate and state friction. We know that when we run dynamic rupture simulations with rate and state, conventional rate and state friction, and we look at the distribution of shear stress as a function of slip at the rupture front, we get curves like the ones shown on the left, which look exactly as any linear slip weakening friction law. So, and this is also theoretically shown that rate and state, when we push the fault beyond a steady state, it produces this linear slip weakening. The fracture energy associated to that can be related to the friction, this rate and state friction parameters, which you see here, the B sigma parameter that controls the amplitude of the state effect, L, which is the characteristic length scale of the state evolution, and the logarithm of the slip velocity, squared. So this gives a fracture energy that is dependent on the peak slip velocity close to the rupture front. There are relations between peak slip velocity and rupture speed that help us convert this into a fracture energy dependent on rupture speed. So that is something that can be done, and then use the crack tip equation of motion to predict the growth of rate and state ruptures. And this is basically what was done in the Rubin and Ampuero paper back in 2005. We were interested in predicting the different sizes of nucleation zones that we were observing in rate and state simulations. And we saw that it depended on the value of the ratio of A over B. And in particular, if A over B is very large, we found a larger nucleation zone that was very different than the previous estimates that existed in the literature. And to establish these results, we actually did a fracture mechanics argument to balancing the fracture energy I showed earlier. So that works very well for rate and state. And there's a very nice recent paper by Dimitri Garagash that goes into much further into the implications of crack tip equation of motions for rate and state. I invite you to have a look at that paper. Now, something I want to emphasize here is that those results are for the aging low, and with the sleep low, things are different in important ways. Here are the sleep weakening response of a rate and state fault, of an aging fault on the left, and a fault governed by the sleep law of the state variable on the right. And each curve is for a different magnitude of a velocity step. And you can see that for the aging low, the apparent sleep weakening distance keeps growing with the amplitude of the velocity jump, but that is not the case for the sleep low. And this leads to a different scaling of the fracture energy. For the aging low, it was logarithm of V squared, and for the sleep low, it's just a log of V. And this seems like a very small feature and difference, but actually it leads to enormous differences in the results during nucleation. On the left, you can see at the top sleep, and at the bottom the logarithm of sleep velocity during nucleation for the aging low. And on the right, you can see the same, but for the sleep low. And the big difference here is that for the aging low, the nucleation produces these expanding cracks, whereas for the sleep low, it very quickly becomes a self-similar pulse. So with much smaller sleep, very different features. So this is to say, maybe for the ones who are doing laboratory friction here, is that doing big steps is important for us modelers to have results of laboratory experiments with big steps to really distinguish between the different state evolution laws that have been proposed in the literature. To close, I want to show also some recent results that are based now on a different flavor of rate and state friction. These are so-called V-shaped rate and state friction laws that at low speeds, they have velocity weakening, and at large sleep velocity, they have velocity strengthening behavior. And in this study, we're interested in slow earthquakes. That's why we adopted this type of friction law that can put brakes on sleep and generate slow earthquakes easily. So we can translate the friction law into a fracture energy relation as a function of rupture speed, which will have the same features. It's a speed weakening at low speeds and speed strengthening at high speeds. So this is derived from the V-shaped friction law. And an interesting feature of this is something that was already mentioned near the end of Dave's talk, that these sort of models produce a first stage of very fast weakening, followed by a second stage that's much longer, that produces continued weakening inside the sleep zone. But here in these models, we are considering these large pulses that have saturated the seismogenic depth. And what we have found is that we can generate a broad range of rupture speeds that are steady ruptures with different rupture speeds. Some are extremely slow, like slow sleep earthquakes, and some are just regular, fast, dynamic earthquakes. And we can tune, you can vary the rupture speed by changing the stress drop or by changing other frictional parameters. The bottom line is that all these simulations that I'm showing here on the left, if properly normalized, they can be collapsed into a master curve, which is shown here on the right, the black curve here, which is predicted by the fracture mechanics theory. And here we were able to do this by putting together in the fracture energy the contribution of these two terms here. So in other words, we didn't need to make this difference between fracture energy and breakdown energy. So that I think is an interesting discussion to have, and we'll have to think about these results and other results to see how to reconcile all those views. So to summarize, let me reiterate the few points I've tried to make here. The first is that we still have an incomplete theoretical understanding of how fracture mechanics, and in particular crack tip equation of motions, can be developed for sleep pulses or pulse-like rupture. However, I gave you one example where we were able to do it, and that's pulses that are caused by saturation of a finite rupture width. So maybe we should take that as one reference point with which we can forge forward. About the contribution from off-fault dissipation, so I think it's well established that for crack-like ruptures, off-fault dissipation will generate a scale-dependent contribution to fracture energy. There's still an incomplete quantitative understanding of that. So what is the ratio of off-fault to on-fault? That is something that we haven't yet completely understood, and it's in progress. About rate and state friction, the important point is that the fracture energy implied by rate and state friction depends substantially on the choice of the state equation. So that invites careful experiments to resolve those questions. And for pulse-like ruptures, pulses that have saturated the finite seismogenic width, fracture mechanics seems to work fine despite the continued weakening inside the pulse. And that's it. Thank you.
Thank you, Pablo. Interesting time. I suggest any questions directly for Pablo, but then sure we'll take a couple minutes for the discussion part. So if you have a question, please raise your hand directly for Pablo. Sorry, I hope my internet is okay. Yeah. Bin Hao?
Thank you, Pablo, for the great talk. Could you briefly describe why pulses would naturally occur in a very long fault?
Pablo, you're muted.
Sorry. So let's imagine first that the top and bottom edges of the fault are pinned. So there's completely locked beyond that boundary. You can think of it as infinitely strong barriers. When the rupture reaches those two edges, the sleep stops there, and the healing front returns to the rest of the fault. Maybe you can see it here at the beginning. There's a curved healing front that is propagating downward and upward. And that just shuts down the sleep behind the rupture front. It's really unavoidable in 3D simulations.
What is the healing front? Sorry.
The healing front is a front that shuts down sleep. So think of it as the opposite of a rupture front.
Okay, thank you.
Okay, I don't see any other raised hands. I invite more questions maybe directly in the chat, and I ask Valère to share his slides for his short contribution to the discussion. Pablo, could you please stop sharing?
Yes, stop sharing there. Okay.
Hopefully you can hear me and see
yes.
my. Okay, excellent.
Perfect.
Well, thank you. I just want to give a very brief contribution of some of our work looking at rupture-dependent breakdown energy in our simulated fault models, including thermo-hydromechanical processes. So as Dan mentioned beforehand, there can be a bunch of other processes that occur within the shearing layer. In our case, we're going to be looking at fault models, including the thermal pressurization of pore fluids during simulations. So these models include just linear elastic bulk with a planar fault and frictional ruptures. But in this case, we look at the evolution of shear resistance, not just through rate and state friction, but also through rapid pore pressure changes coupled to shear heating. And so the main point that is particularly relevant for our discussion here is, as previously shown by other work, such as in Rice 2006, depending on the permeability of the rock, if you have this active thermal pressurization, you have potentially continuous weakening of shear resistance with ongoing slip, which is particularly interesting. If we imagine the breakdown energy being the integral down to some minimum resistance level, essentially you have increasing breakdown energy with slip or time. And so this simple theoretical predictions have been used has been one mechanism that is considered consistent with this inferred increase of average seismological breakdown energy with increasing rupture size from natural earthquakes and average slip here. But this change or continuous weakening is also an interesting key point for this critical issue between frictional ruptures and linear elastic fracture mechanics, namely that there is no defined dynamic resistance level. And so it's not clear what level of friction energy to just drop out of the problem here. In particular, weakening when we have shear heating is coupled to the absolute levels of shear stress. So while in fracture mechanics, we like to think of the fracture energy as the relevant dissipation to the governing rupture propagation. In this case, weakening is actually controlled by the overall absolute level of stress and overall dissipation here. The other key point here is that as we have this continued weakening, while we can define the breakdown energy at the end of the rupture, this weakening is not localized at the rupture front, as mentioned beforehand or in previous talks. But given this, if we look at the average breakdown energy shown here in red from our simulated ruptures, they do match this increasing trend with breakdown energy with slip. And so one might have the idea that maybe we can still have a simple relationship of slip-dependent breakdown energy. But if we look at the local breakdown energy for points throughout the ruptures shown here in yellow and blue, this actually becomes much more complicated, where you can see variations by order of magnitude for the same amount of slip and breakdown energy. And so this is the last point I just want to emphasize here. Then our fault models with thermal pressurization, this breakdown energy is certainly not a fixed fault property, but it's also not even a unique function of slip. So I'm showing here are 3 simulated ruptures from the same fault model, all with uniform hydraulic and frictional properties. And these 3 ruptures have the same average slip, average stress drop, and average breakdown energy. But if we look at 2 points here in blue and yellow and look at the evolution of shear stress with slip in the 3 different ruptures, the variation, the weakening process can be very different from rupture to rupture. And in fact, if you look at the local breakdown energy, just defined down to the minimum, it can increase with increasing slip, it can decrease with increasing slip, it can have very different relationships from rupture to rupture for the same point along the fault. And this is because ultimately the weakening doesn't depend on the final amount of slip, but how that slip is achieved, not just based on the local pre-stress and properties, but also through wave interactions throughout the entire rupture. So this is just one thing for us to keep in mind is in terms of defining this quantity, we can define it and calculate it and look at trends, but it's not necessarily intrinsically linked to it's not an intrinsic fault property in itself and not a unique function of slip in itself. So that's all I really wanted to share today. Thanks so much for the time.
Super, thank you very much. Massimo.
Yeah, actually, I have one question for Lambert and a comment that I will do later on if we have time. Valer, one question. Did you compute which is the thickness of the thermally and hydraulic activated layers in your simulation? Do you have an idea how wide is the thermally activated layers?
Okay, so in terms of actually the diffusion scale over the duration of the layer. So it's interesting. So basically, we prescribe a shearing layer in itself to calculate the temperature change, but I have not actually looked at what the diffusion thickness would actually be on the time scale of the layer. In these cases, these ruptures end up being crack-like. So the simulations are on the order of 1 millimeter to 10 millimeter. And essentially all the heat and even fluids will be trapped within that. So it's going to be on the order of 1 millimeter or less on the time scale of rupture.
So, okay, extremely thin.
So within 1 to 10 millimeters.
And also the hydraulic diffusivity, the hydraulic activated layer, it is so small.
For these simulations, it will stay within the hydraulic diffusivity is somewhere between, it varies from simulation to simulation, but it can be between 10 to the minus 6 to 10 to the minus 3 meters squared per second. And typically on the time scale of ruptures, the fluids will stay maintained within that shearing layer of 1 to 10 millimeters.
Because the origin of the question is to make, again, reconciling with geological observation. Because if the thermally and hydraulically activated layer are thicker than the fault core boundaries, for instance, it is clear that in realistic case, your pressurization is even higher if the fault core is an impermeable barrier. And therefore, this will strongly affect the weakening and the stress drop.
Yes, so the shear is, we assume a Gaussian shearing layer here. So there is some notion of spatial variability and diffusion within that layer. It's not perfectly just an adiabatic solution, or adiabatic undrained solution, but the overall, the diffusion scale will stay within that 1 to 10 millimeter.
Thanks.
Okay, Chris, if you have a quick question, you can go. We also have Camilla Catania will also present some slides after.
Okay, I have a quick question. I also want to make a point. I don't think we should be off by more than 10%. 10% is very good. In our time.
You mean in terms of timing?
120 minutes. So that means, according to me, we have 8 more minutes.
Okay.
And, yeah, so I will save my question for tomorrow. But,
all right.
Yeah.
Okay, so the plan is I have 2 quick slides I promise to share, and then after me, Camilla will be ending the session as our highlight speaker. So let me share my screen. Okay, so I want to introduce very quickly some recent work that we've been doing with Dimitri Garagash and Dahuzi and Martin and Mai and Kadek Pagonadi at KAUST. And we've seen this plot a lot about scaling of fracture energy with slip.
We don't see, Alice, we see black. Maybe you need to push one screen over.
Right. How about this?
Yes.
All right. So we've seen this scaling a lot of fracture energy with slip. And we heard the question a lot of maybe why fracture energy increases with both event slip and event size. And there's a couple of hypotheses. And we are basically introducing that maybe 2 mechanisms are working together depending on different length scales. That we have a weakening process cascade with governed by a small slip fracture energy, so more classical concept of fracture energy, which is well defined by a DC, so a classical well-defined length scale. And we have followed by processes governed by continued weakening, like a large slip fracture energy that's fault invariant, so not a fault property. And if we are plotting the same quantities that have been plotted in Vieska and Garagash, not as fracture energy versus slip, but as fracture energy versus source radius, we actually see this kind of diffuse cloud, which doesn't tell us very much about the potential scaling of fracture energy with fault size. So what we've been doing is that we revisited the inferred fracture energy of especially the smaller events. And we've been developing, and that's mostly Dimitri's part, a physics-based model for fault frictions, which are governed by fast velocity weakening. weight and state friction, which allows us to correct for the re-strengthening effect during coseismic rupture. And if we're doing that, we actually get an emergent linear scaling of the minimum fracture energy, which with source radius or with fault size. And we've been using this emergent linear scaling. So in gray, we have the uncorrected values, and in colors, it's the same events, the small earthquakes from this catalog now being corrected for coseismic re-strengthening. And we use this emergent linear scaling of the minimum fracture energy with fault size to model dynamic rupture simulations across fault damage zones of up to 1,000 fractures, which are distributed around the main fault. So there's a couple of nice examples that I will not go into, but one of the examples I would like to show you, and that is an animation here showing slip rate of earthquake cascading only in the damage zone, which is something that you could term a mode 4 dynamic rupture with specific characteristics such as the fracture cascading rupture effectively suppressing main fault rupture dependent on the orientation of this pre-stress ratio. So under other pre-stress ratio, other orientations, you would see fractures being able to trigger the main fault, or we have earthquakes of the equivalent slip as a whole main damage zone. And this is already the summary. There's a recording of a longer version of this talk, which was given for CIG by Dimitri a couple of weeks ago. But in summary, basically what we are proposing is that the seismically observable fracture energy can be actually decomposed into two parts. One is fault size dependent and potentially a small slip part, and the other one is potentially fault invariant, the large slip part that increases continuously with coseismic slip. And we think that the nucleation of dynamic slip on a fault would be defined by the small slip fracture energy. And we also come up with this proposed scaling of this minimum fracture energy, which is of course the relevant part if you want to understand the nucleation dynamics that would scale the fault size and that allows for seismicity on all scales. And if we're doing that in 3D dynamic rupture simulations, what we find is a whole range of behaviors, the main fault rupture, including off-fault seismic slip or cascading dynamic rupture on fractures in the damage zone with or without activating the main fault. And then this also led us to revisit that famous plot of Craig McCluskey and proposing like some more detailed mechanisms of what we could actually see here, like a slow cascade followed by a fast dynamic cascade kind of effects. And yeah, with this, since we are short in time, I will post this link in the chat, and I will hand over, I think, directly to Camilla.
Hi, thanks for the chance to share a couple of slides. I prepared these slides because some of the material we heard in the previous talks I thought was a very good introduction, and I wanted to offer a slightly different perspective. Specifically, often when we talk about fracture energy in terms of observations and how they help us understand earthquakes, we're thinking about the dynamic rupture. So I wanted to say a few words about how fracture energy can also be useful to understand earthquake statistics, including the recurrency interval and the frequency magnitude distribution. And this really builds up on what we've heard from David and Pablo. So we learned that from linear elastic fracture mechanics controls both nucleation and rupture arrest. And we can think of the elastic energy provided by loading throughout the cycle as the energy source that has to counterbalance the fracture energy. So now we can then think about a time scale during which we accumulate enough elastic energy to allow for earthquakes to nucleate, and then a different time scale that will control how long do you wait after an earthquake for an earthquake to be able to propagate a given distance, which will depend, of course, on the fracture energy. And one study where we used this idea, we were looking at small repeating earthquakes. And we were discussing earlier if this linear elastic fracture mechanics, it seems to work really well in the lab, can it also work in nature? And in this study, we find that using these two different criteria for nucleation and arrest, we can reproduce the recurrency interval of small repeating earthquakes and how it scales with earthquake moments. Specifically, the recurrency interval of repeater scales with the moment to the power of 1/6, which is not predicted by simple models, but fracture mechanics predicts the right scaling. So this is kind of encouraging in terms of its applicability for real earthquakes. And then another implication is that because these time scales depend on the size of a seismogenic source, when these two time scales diverge significantly. So when it takes a lot more energy for a rupture to propagate across a source than it does to nucleate, you get more partial ruptures. And so this is a well-known result from simulations. A number of people have found the same behavior. A paper by Sylvain Barbeau came out in the same year, showing a transition between periodic characteristic events on small faults to more a wider distribution of events and more aperiodic behavior on larger faults. And so what I wanted to highlight here is that you can explain this behavior based on fracture mechanics. And that's, to me, that's one more motivation why we really want to understand fracture energy. And all the work I've done so far uses rate and state friction with the aging law, which as I'm sure we will hear more about, is one case, and it's very simplified. But so as we learn more about this, we may be able to not only understand earthquakes better, but also earthquake sequences and the statistics. And that's all.
Thank you. So Chris, you're the boss. Should we stop?
Georg already has his hand up, and we could do a little bit. I suppose I would like to preserve energy for tomorrow. So yeah, let's go for a few more minutes, but maybe not more than 10. How's that sound to you?
I can postpone my question for tomorrow. No problem.
Yeah, but I think, we don't need to quit instantly, but I think we should respect our time scale so that
Okay, Alice. So what is your small scale and large scale fracture energy physically? I mean, what kind of physical mechanism do you attach to these different terms?
Yeah, that's a good question. I have lots of slides that I couldn't show. So this is an example, I hope you see it, of what could be like this difference between the small and the large scale one. So we think that the small scale one could be correlated to the strain localization process, and that at some point saturates, basically, which is dependent on the width of the gouge, and that defines our minimum fracture energy. But then after that, we have weakening processes like thermal pressurization kicking in that are not limited in terms of scale. So, and that is kind of our idea of why we have these two processes.
Okay. Thank you.
Other questions?
Did we scare everyone away from asking questions?
I think we should preserve the energy then. And thanks everyone for contributing. Yeah. And I know Francois also had some slides, but I think he also preserves them for tomorrow.
I can take it for tomorrow. It's better.
Yeah, thank you everyone. See you tomorrow. And yeah, I think that we should also keep in mind what we really keep thinking what we discussed today, because tomorrow we will further go in depth on these issues.
Exactly. Yeah, we're not going very far away tomorrow, right?
Yeah, but we are going to the lab, okay? And therefore now we have the constraints from the modeling and the constraints from the geology, which is quite a realistic constraints. So for instance, what Alicia was discussing about the scales, responding to Georg, okay, how will we control this in the lab? So do we see the scaling from one scale to the other, this passage, and how we measure these processes in reality? So far in the lab, we were unable to model the transition from one mechanism to another one.
Thank you. Great.
Okay,
thanks to all the speakers.
Bye-bye. Thanks to everyone.
See you tomorrow.
See you tomorrow.
See you tomorrow. Ciao, ciao.
Bye.
Bye tomorrow.
Thank you.
Tomorrow.
Bye.